Sawhorse projection, Newman projection, and Fisher projection. And yesterday we have also looked at butane conformations like anti and gauche or at the same time eclipse kind of conformations we have seen for butane, and that is a very important question, as I told you earlier only. There are also some small simplistic or simple strategies where you can do an interconversion from Sawhorse to Newman or to Fisher projection. Okay, so first thing, if you have a Sawhorse projection, okay, Sawhorse you are already aware, inverted Y and Y, you will be having, this is the stereo center, and these two carbon atoms are connected. Okay, when you have multiple carbon atoms which are connected, you can easily mention Sawhorse projection. So all the time look for front carbon, rear carbon, from where we are viewing it. If you are viewing from this direction, this becomes the front carbon, this becomes the rear carbon. So identify the carbon, front and rear. Then go through the, if you view from the front carbon, if you want to make a Newman projection, keep a dot and keep other functional groups. Okay, phenyl, bromo, and hydroxyl group. Now you see phenyl, methyl groups are in opposite position, front carbon to rear carbon. So make sure that the rear carbon by a circle and keep methyl group, amine, and chloro group. Okay, so this is the staggered configuration. You can easily identify because phenyl, methyl are opposite. If methyl would have been in the same direction as that of phenyl group, then you can have a eclipse kind of conformation. Now it is a staggered kind of conformation. Now you make sure that the front carbon, okay, front carbon is dot. This carbon, you are turning by 180 degree. Why you are doing this? To make a Fisher projection. Okay, so you make it like 180 degree rotation, so that what happens, phenyl group will be in the same position as that of methyl group. Hydroxyl will be in the same position as amine, because you can see you are literally turning it out 180 degree. So methyl, phenyl, hydroxyamine, and bromo and chloro groups. Now you can easily identify. Again, you remember from which direction we are viewing, phenyl or methyl. Those are the ones in the vertical lines. Vertical lines are away from you, and horizontal lines are nearer to you. So now what you can see, hydroxyl, bromo are in the horizontal line. That is the first carbon because dot. Okay, and rare carbon, amine and chloro group, second carbon, and you have methyl group as vertical line, methyl and phenyl. Okay, so this way, given any kind of projection, okay, Sawhorse, Newman, or whatever projection is there, you can easily interconvert into different forms. Okay, identify which is there, which is the carbon, from which direction you are viewing, and make it front carbon and rear carbon, and accordingly you may classify. Now, yeah, this is what we had yesterday discussed. Also, this is the total outcome what we have discussed. Fisher projection to Newman projection. Okay, so this is the Fisher projection, and you can make a eclipse kind of conformation. Okay, so vertical lines represent the things which are facing away from you. Okay, so now black and red are the ones functional groups which are facing away from you. And if you want to make a Newman projection, you make an eclipse, you convert into a staggered kind of conformation. So you can see all that is the front carbon, okay, and accordingly the rear carbon, and then you can do. All the time remember, Fisher projection, you talk more about eclipsed kind of conformation, okay, and whenever you have Newman to Fisher projection, make sure that you convert staggered conformation into eclipse confirmation, then accordingly labeled. Okay? So this is also an important and probably little bit extended part as compared to your earlier schooling study or like a plus 2 level study on conformations or stereochemistry. Now, yesterday we were also talking at the end of the class on what is called as how to label or how to identify the numbers or how to give assign numbers for a chiral or any molecule, whether it is R or S. Okay, so based on this, these descriptors, these stereochemical descriptors, which essentially is an absolute configuration, like R or S, which is rectus or sinister, which essentially is the Latin words for clockwise and counterclockwise. Okay, you know, like R means clockwise, S means counterclockwise, and these RS nomenclatures are essentially originated from Kahn, Ingold, Prelog. So even this part we have discussed, and these are the important sequence rules by which you can essentially create absolute configurations. Okay. Now, I want in the class, any one of you, can you name probably like one by one, can at least 4 set of rules are there. Whatever you remember, can you just give a try on what are the set of rules about CIP rules? Anyone? I think yesterday few of you could answer that already, but whoever are aware of it can answer. Anyone in the class who like what exactly I'm asking is, how do you assign the priority for various? Yeah, go
Sir,
ahead.
the more the atomic number, the greater the priority.
Yes, so more the atomic number, you will have high priority as compared to carbon. If you have other atom, that will get the first priority. And any other, so means
Yes, sir.
what essentially others are telling is, if carbon is, for what reason we give one and why we make it as R or S is because it has more atomic number than carbon. That is what one we refer to. Yeah, any other point?
Sir,
Yes,
after
sir.
that we must check the molecular weight.
What is it after the functional group or
After the atomic number, if the atomic numbers are same, we should check the molecular weight.
molecular weight? Okay, okay, that is also, let us make it even more simpler by looking at the next functional group, what he has been bound to. Okay, if you have a competition between them, then look for the next adjacent carbon or like that, or adjacent functional group where you can assign. That is also a point which you can note. Any other specific suggestion?
Sir, if isotopes are there, then greater the mass number and the more the
Yeah,
priority.
yes. That is also, yeah. So again, essentially, it moves around molecular weight and or the functional groups for what has been assigned. Now, let us look. See again, this question you can expect for in a 6 mark question or 8 marks question with a combined one. So they can ask you what is or discuss about CIP. C stands for Khan, Ingold, and Trilog. Okay, so whenever you are writing, you should also expand it. Okay, do not just state away CIP, don't write. You can mention CIP rules or Khan, Ingold, Prolog rules are based on 4 important assumptions. Okay, and these are the 4 assumptions. And you can also give an example so that it will be easier. Now, so I think all of you are aware of one rule very confidently, that it is essentially based on atomic number. atomic number is the key. Okay, and functional groups you will go only when you have the next functional group which has been assigned. Okay, so even this part I think many of you are already aware of. Now, so even this I told yesterday. So these are the full names. You need not remember the full names, just for your like understanding of how various like researchers made for what reason we need to have an absolute configuration. Okay, they are able to get the optical activity, but they are not able to make a generalized set of rules. These three people together formulated some set of rules. What are those? Let us see. Again, everyone, please pay attention. Okay, if you have a paper and pen, you can also take down, and then accordingly. And as I told, this is a very important question. Like in organic chemistry, very few sets are very important, like isomerism and all. Even CAP rules are very important. So here in CAP sequence rules, first thing is you assign priorities for the substituents. Substituent means if you carbon is the standard, like stereo center, it is linked to 4 different functional groups. So this you can call it as ligands. Okay, now assign the name based on how this position of the substituents. So as all of you already aware that the ligands with higher atomic number will get higher priority. Obviously, when ligands with lower atomic number will get least priority. Okay. Again, you can see a broken line like this and thick line. Bromo and fluoro groups are facing towards you. Chloro and hydrogen groups are away from you. Okay. Now, how to give? Among bromine, chlorine, and fluorine, bromine has got the highest atomic number. Assign that first. And hydrogen, since it's least number, you can even keep it far aside. Okay, to make 1, 2, 3 in the same plane. Bromo, chloro, fluoro in one plane, and hydrogen away from you. You can make it. Okay, like a planar kind of situation. So first assignment you can do for bromo. Then obviously chlorine is the next highest, followed by fluorine. Now 1, 2, 3. If you have like this, the sequence is R. You can write R like this, right? One line and followed by R. So this is R assignment. How you can get it is by looking at the atomic numbers. Let's say you flip fluorine to bromine, bromine to fluorine. Keep chlorine and hydrogen intact. Again, keep the hydrogen as such. Okay. Now whatever you have bromine here, you make it here. So bromine, chlorine, and fluorine. Now you see the assignment. 1, 2. 2 remain same. Only we are flipping bromine to fluorine. So it goes anti-clockwise. So you know that if it is clockwise, you call rectus, and yes, you can call if it is anti-clockwise. So you can see here, it goes in anti-clockwise direction. Okay, so counterclockwise. So just by small interchange, flipping up of these two atoms, you can make R and S. Okay, so this is the first set of rule. The take-home message is high atomic numbers will be high prioritized as compared to low atomic numbers. Okay, now if there is a tie, okay, you can see here CH, CH2, CH3. So obviously, which one we should take now? We are doubtful. Both you have carbon. So if there is a carbon means go to the next atom. Go to the next atom along the chain, and then you observe rule number 1. So now you can see here CH2OH, CH2CH3, CH3. So compared to ethyl and methyl, ethyl one is more high atomic because you have 2 carbon atoms. Here you have 1 oxygen atom. Okay, so what you do, first priority is this. Again, hydrogen you can neglect, you can keep it outside, away from you, and keep methyl CH2OH, CH2CH3 at one place in a plane. And then what happens? CH2OH first priority, second priority CH2CH3, and third priority CH3. Okay, so now you can see how the assignment goes 1, 2, 3. It is counterclock wise direction, so it is yes. Okay? So this is the second set of rule. Okay, even I think you might be aware of this kind of rule, but for that reason I told that if there is any tie, like if both the atoms are same, then we go for the second atom. Now, if you have something like this OH, CH2OH, okay, or COOH and methyl group. In this case, all the ligands in this given sphere, first you should explore them before going to the inner sphere. Or for example, you should follow principle of outward exploration. Okay, now what exactly is this? Carbon attached to OH. Okay, C attached to OH. Now C attached to C, OH double bond O. If you have C attached to COOH, how you can write it as C double bond O, single bond OH. So you don't think that here you have two oxygen atoms. It means it is first priority and this is second priority. Okay, carbon attached to directly oxygen group because higher atomic number is first, and then the second, and third one is carbon attached to hydrogen. Okay, so now the absolute configuration is yes. So how, like what exactly we were discussing is assign the priorities like this. So you can see here, which is if you have a direct contact like with oxygen, give the assignment first, and then in this you can again go to inner functional groups. Okay, like 3-1, 3-2, 3-3 accordingly. So first you finish the inner sphere before going to the next sphere. So again, for this you should write what is the absolute configuration. Even this part, I think it should be clear enough. This is the third set of rule. Next comes double bond. Okay, I don't know whether this you must already read or it might not have struck. Is if you have a double bond or a triple bond, you consider it as a triplicate or duplicate of the species. If you have double bond means C bond to O, C bond to O. It is essentially right, no? The C double bond O means C is bonded to oxygen twice. So you have written like that. Okay, do not worry about the single bond and the double bond. Single bond in the sense like sigma bond and pi bond. You are supposed to write compared to carbon which is bonded to only carbon. Okay, so if you have double bond, you do 2 times. If you have triple bond, you can write 3 times. And accordingly analyze. Okay, what is the set of rules which you can follow it up. Next, as we have shown in the first rule is if you do, what are the permitted changes in CIP rules? Like if you can see that bromofluorine, if you change, we can change from R to S. Okay, in the first slide we have already seen like bromeo. Again, for various reasons, you can keep hydrogen far apart because that is the least priority. Okay, wherever whichever position is there, that will be the least priority. Based on other things only you can assign. So what exactly we are talking is double exchanges or 2 successive exchanges in Fisher projection will be having same configuration. Means you already exchanged once. Again you do second time exchange. Then you get the same structure whatever you have started with. Okay. Same structure means the assignment. So now you can see for the chloro-bromofluoro counterpart, these both are kind of enantiomers. Now, we have already seen in the beginning that if you interchange one of the ligands in Fisher projection, we get opposite enantiomers. R will become S. Now, let us go into details. Let us see if you interchange one set of ligands in a Fisher projection, it will lead to opposite enantiomer. Already we have seen in the so what essentially you have done here is you can see from hydrogen you have moved with an angle. Okay, hydrogen fluorine, like what I had. If you everything you turn now, if you go more into details, for example, you have lactic acid. Okay, which is generally used for like curdling of milk and other generally the process. You can see here carbon attached to OH, COOH, CH3. So these three are the high priority. Assignment obviously 1, 2, 3. So it is S kind of configuration. Now what you do, interchange OH with H. Okay, if you do, you get R, because you see this is CH3 hydrogen are coming towards you, so then it becomes R kind of assignment. Okay, it becomes R enantiomers. Now, if you rotate Fisher projection by 90 degrees in either direction, either right or left, okay, which changes the chiral center. For example, now we have S lactic. For example, the form is S. If you make it like a 90-degree counterclockwise rotation, so OH you are moving here, hydrogen comes here, COOH here, methyl here. We get R lactic acid. Okay, so essentially how you are writing phi is, you can see here, OH, COH2OH, this is away from you, methyl is towards you. So hydrogen, these three you can put in one plane. Even in that case, we get S kind of arrangement. In the case of this lactic acid R, COOH was coming, whatever was there, it becomes here. So as if you keep everything in one plane, okay, you get R kind of assignment. Okay, hydrogen leaving aside. So what essentially we are looking at here is, if you rotate Fisher projection by 90 degrees clockwise or counterclockwise direction, you can make enantiomers. If you get R, you get S. If you are having S, you can convert into R. Now, if you do a double exchange, so what happens? One like 90 degree, again 90 degree if you do a rotation, then you get retention of the configuration. Okay, so you can see that you have lactic acid. Now you can rotate by 180 degrees clockwise. So whatever COOH is there, it comes down, hydrogen goes up, and OH here will change to here. Still it is S kind of configuration. So you can see here both top and bottom. Before doing 180 degree turn, after doing 180 degree turn, the configuration is intact. Okay, now also you can see for this 3 lactic acid structure, now you can keep COOH in one place and then you can like rotate other ligands in a clockwise OH H methyl group here. Even this has got same kind of arrangement. Okay, so which essentially means if you do double exchange or two successive exchanges, we can retain the configuration. Okay, so that is an important point which we these are all like extension of the CAP rules. Okay, now, is there any doubt till here? Anyone in the class? Any you have any doubt or on this? What we had discussed? Yeah, today I'm going to definitely upload the handout because today only we'll be finishing the stereochemistry. So, any doubt to anyone, or you will be. So again, we were talking about CAP rules, where we assign the functional groups based on atomic number and based on the inner sphere, followed by if there is any equivalence in that, then we go to the next set of carbon atoms. These are the main things in the CAP rules. But if you do a double exchange or accordingly in the functional groups, we can retain the configuration accordingly. So is there any doubt to anyone? Yeah, Amitoj, Ileraj, Uday, Shaz. Any
No, sir.
doubt?
Nothing,
No,
sir.
sir.
Okay. So anyway, as I told, I'll upload the handout. Look for it. Okay. If you have any doubt or clarifications, you can ask. But again, I'm telling you, stereochemistry, you should definitely practice it once. Okay. Yeah, it looks very simple when you do in a PowerPoint hearing and all, it looks fine. But when you practice, because you want to draw those things for your exam, so it is very important to understand and accordingly plan. Yeah. Okay. How about Ayyappa Reddy? Did you understand Ayyappa Reddy and Uma Venkat?
Sir, yes, sir.
Yeah. Okay.
Yeah,
Fine.
sir.
Okay. Fine. Okay. So again, I'm telling you, everyone, if you have, if you don't get it, you can ask me, interrupt me even in between the class. If you feel a bit hesitant later, okay, last 5 minutes also you can ask, or you may contact me and ask. But don't lose out any, for example, any points. Okay, because these are all basics, and I can say that 70% of or even 80% of whatever I have taught now, you must have read in your earlier class. Okay, probably they might have directly read, you might have read from a book or like that, but now we are just making it more simplified by keeping some set of rules. Okay, so as I told, please understand and all the time practice, especially stereochemistry. You should definitely practice. Now, let us go to a very important set of topic. Okay, probably from last 10 minutes or till 12:25 I think we have class. So till that we can. So now what exactly are you seeing in this slide? Like if you see these 5 images, what is that thing which strikes to your mind?
Division, sir. Symmetric
Huh?
division. Symmetric
Symmetric,
division.
yeah, Uday, yeah. So symmetric division. Okay. So what exactly is symmetry? So now, can someone tell me in all the 5, like what kind of symmetry it is? All the 5, or one common symmetry, or yeah. Or for example, people can also tell me now if you won't get what exactly symmetry here, what exactly symmetry correspond to?
Same, looking same.
By exchange, it looks same. Okay, so I can take the word same Yeah, go ahead, Shashank.
Vertical symmetry, sir.
Vertical symmetry. Okay. See, vertical is a very, very general word. Okay, let me take even that is also okay. Yeah. Any other? No, I'm asking also others. What do you mean by symmetry?
Sir, it means dividing a shape into two identical parts.
Dividing a shape into two identical parts. Okay. See, when you give a definition now with respect to this, whatever I have shown now, that suits well. Okay, whatever you can divide into two halves and we get same. But if you want to get a deeper insight, okay, we should define accordingly to give a very generalized. So now, from whatever few of you told, Uday, Shashank, Tarun, or whoever other people have raised, all told that the words same, vertical symmetry, and we get the same kind of patterns, the same set of arrangements. Okay, if you do twice or thrice. Generally, I think many of you are already aware that nature loves symmetry. Okay, so that is the reason mostly we like I don't know because I used to when I used to study my PhD and all we used to give we were given an example regarding generally nature loves symmetry even for a newborn and other things. When they are born, they'll perfectly symmetric and all probably face and other things. In order to break the symmetry, okay, they put some that dark dot, okay, at one place, left or right or whichever, okay, or so which essentially is you are breaking the symmetry. Okay, but you see major things. Okay, it all the cases we like nature generally loves symmetry a lot. Okay, now in the form of butterflies anywhere you can see. So now what exactly we are looking is line of symmetry. Okay, why, you may be wondering, for what reason we are studying symmetry in stereochemistry. Okay, let us see what exactly is symmetry all about. So in symmetry, how do you talk about is, it is the concept which describes geometric properties of macroscopic as well as microscopic objects. You can take like a tree, okay, or even like even for example Taj Mahal, which is a very large object, or even for a microscopic object. For example, a molecule of ethane or methane like that. Okay. So that is the reason we are jumping from a very high level object to a smaller objects. That too, why we are so much keen is we are looking at molecules. Now, in order to discuss symmetric properties, we use a shorthand notation called point groups. Okay? And again, please, we have a very small topic on symmetry. I do not want to discuss more about it, but as I told, I don't mind discussing it when required also. By combining point groups and some symmetry operations, which we can make a molecule M into a superimposable one. So what we are trying to do is, as some of you told, we want to turn, rotate, invert, whatever you do, make sure that it comes to the original shape, okay, which is superimposable. Now, let us see what exactly is symmetry all about. Okay. Now, as I told you, we can do an inversion. We can do we can do like translation. Okay, or we can also do like like rotation, glide, so many are there, but we will not discuss more. So a symmetry operation, how you can define is by permutation, and which transforms a molecule into an arrangement of atoms indistinguishable from the original. So whatever you have started with, by doing some changes, okay, by like rotation, okay, or whatever you do, make sure that it becomes indistinguishable. So you started it, the same thing should be turning out, but you have done some rotation. Okay, all those things. Now, what are the possible permutations you can do? Especially, you can do translation. Means translation means you have an object here, you move it further, like x to x plus y, or you can like rotate, or you can do a reflection. Take a mirror, you get a reflection, and inversion. For example, now this carbon, this blue ball and the corresponding red ball are inverted. Okay, and of course it's not only these four, but you can combine them. Any of this, if you do, you get symmetry. Now, especially in molecules. So many of you, this is the simplest example you can think about. A fourfold, probably after the class you can try. If you take our hand and you do a 90-degree rotation, 180-degree, 240, 180, 270, and then 360, we can retain the hand to the original direction. Whatever you have started with, you end up into the same position. Okay, by doing 90, 180, 270, and 360. So that is essentially fourfold of rotation. Okay. So how can you say your hand is symmetric? Okay, not both the hands, one hand. Symmetric is by doing a fourfold rotation. Now, as some of you pointed out, a vertical axis. Okay, how to define a generalized term? So what essentially we are looking is symmetric axis. So what we do here, there is an imaginary symmetric axis around which the rotation 360 by n. So whatever object you take, okay, whatever you take, like a pen or irrelevant, whatever you want. If you do a 360-degree rotation, it can come back to the original shape. Okay, so that you're all aware of. But if you do a 180-degree, it will become inverted. So how do you define symmetric axis is how you rotate an object into indistinguishable form with that of original. That is essentially called as symmetric axis, especially 360 by n. Very, very important, 360 degrees, because it is same as what you have taken, whatever object. You take your phone or pencil or whatever form. 360 degree, if you rotate, it becomes to the original shape. That is called as n-fold rotation axis. So how you do abbreviate is Cn. So you are doing n-fold. So if it is n equal to 2, how much will be the angle? Anyone in the class? What happens to the value when n equal to 2?
180.
180. And in n equal to 3?
120.
120 and 90 and so on. Okay, now you can really catch up what exactly I'm trying to say. So 120 degree, 90 degree, 180 degree. When we hear all these terms, we know the bond angle. Once you know bond angle, you make sure that that rule you apply for symmetry. Okay, so as simple as that. Now you can see here, do not get confused, or it's very straightforward. In all the cases, we are looking at axis of symmetry. So you know water molecule. Okay, so water molecule, how you make it, like for example, yeah, this is like water molecule we have. Okay, now if you rotate like 180-degree, okay, it becomes symmetry. If you do like 90-degree, it is not symmetry. What you started, you are not, it is not the same. So if you do 180-degree rotation, then it is symmetric. Okay, so how you do symmetry is, we are turning with respect to this, see the blue ball. Okay, so this is the line of symmetry. So if you pass a line through this ball and if you do a turn, then it is C2 symmetry. C2 means 360 divided by 2, 180-degree rotation. Now C3. So now you can see, for this, 3 Cl groups are angled at 120-degree in one plane, or a triangle, you can easily think about it. Okay, around CH axis, if you do a threefold rotation, threefold means 120-degree, like 120-degree, you get same configuration. Okay, so if you want, I can probably, yeah. So, okay, I don't have all the carbon atoms, but let's see, yeah. Okay, so you can see here, this is the hydrogen which is placed, or like this you can consider hydrogen and the chlorine. Assume that these are all two chlorines also. Now you can make the, because these three forms a triangle. So if you do a 120-degree rotation, which makes all the chlorine atoms same, so it is C3. Same way for benzene molecule, you can have C2 across the axis and perpendicular to the axis. Okay, in any forms you get C2. But if you are looking in between the axis, especially through the ring, we should do, since it is sp2 hybridized, and also you can see that we can have 60-degree turn. If you do, then only it will be symmetric. For example, one turn, so this line becomes here and this will go here. Okay, and for like for example, dichloroacetylene. Okay, so this is infinite symmetry, means whatever you do that, yeah, I think so like this. Okay, so this is infinite mode of symmetry, because you are already having a linear kind of molecule. But if you make the line which is passing through the triple bond, you do a C2. C2 means 180-degree rotation. And even if you pass it through the center also, it is C2 kind of rotation. Okay, so these are different examples of why we want to introduce symmetry into organic molecules. Okay. So I guess I shall stop at this stage. Okay, probably we can even be discussing in the next class. Is we can also have center of symmetry. So you can see here for ethylene molecule, this hydrogen and this hydrogen are inverted. For example, this is +1 means this is 0, -1. I'm just telling you an example. What is exactly the inversion? So inversion is a point reflection. So this point is being reflected here. Okay. So if you consider this as the single point, center of symmetry, you can see this is the blue ring and this is the inversion. Same for hydrogen, black hydrogen. This is the center of inversion. So this is the point at which you see an inversion. Okay, so it is reflection in inverse. Okay, same way you can see now this transition metal or coordination complex. Chlorine is away from you, amine is away from you, and dark bond, chlorine and amine are towards you. Okay, like a 6 coordination number, octahedral kind of complex. You can easily see that if you do this, chlorine away and chlorine are inverted. So the chlorine reflection, point reflection is here. Amine point reflection is here. Okay, for hydroxyl point reflection is here. Okay. So this blue ring is referred as operation of inversion. Okay. Yeah. So is there any doubt on this particular topic? Anyone?